Here we go, Chapter 7 exercises. Problem number 1. A radar unit is used to measure the speed of automobiles on the expressway during the rush hour traffic. The observer measures the speed of randomly selected 76 cars and obtains a mean speed of 62 miles per hour. Now, do you recognize this problem? Or have you seen something similar? I hope everybody recognizes this problem from Chapter 6 exercise set. A radar unit is used to measure the speed of automobiles on the expressway during the rush hour traffic. Exactly the same as before. Now the second sentence differs a little bit. It consists of 3 conditions. The speed of individual automobiles are normally distributed with a mean of 62 miles per hour. Condition number 1, we are talking about normal distribution. Condition number 2, the mean of the normal distribution is 62 miles per hour. Condition number 3, this normal distribution is about individual automobiles. For example, if the speed of individual automobiles are not normally distributed, for example, if it is skewed to the right, for example, then you cannot get correct answer using normal approximation in any of these problems down here. Now let's go over to Chapter 7. In a second sentence, do we have something similar here? Well, 62 miles per hour appears, yes, but then again, did I assume anything about normality here? Is there anything about normal distribution in the second sentence or anywhere else? You don't see it. Does that mean this is not a normal problem? It is something else? Well, the answer is this still is a normal problem. The reason is we're talking about randomly selected cars. So randomness actually allows us to consider the normal distribution, or in this case we have to say normal approximation. The randomness is nice because of those randomness, and we can assume that each selection is not related to the other and it is done in exactly the same environment. So basically we are doing the same thing over and over again. Now there is a nice thing called the central limit theorem in mathematics, which is basically the fundamental theorem of statistics. And the central limit theorem goes kind of like this. No matter what kind of probability distribution you start off with, if you do the same thing over and over again and take the average, that average can be approximated by a normal distribution if the repetition is done sufficiently many times. Now 76 cars, is it considered enough? Yes. According to our textbook, in 1000 level we'll say enough. Personally, I like to have a sample size of 100 or bigger, but anything above 50 is acceptable. Okay, the 62 miles per hour. This is not the kind of number that is carved in stone like the previous problem. We did not assume that the mean speed is 62 miles per hour in this case. What we did was the 62 miles per hour came from the sample study of 76 cars. So the real mean, maybe a bit higher or maybe a bit lower, maybe quite a bit higher, even though the probability for large deviation will be probably small. But we can consider all kind of situation. And we have to answer all these questions about the mean speed, the real mean speed, which we don't know. And of course, we cannot find out precisely. There's nothing accurate in statistics. So everything will have a give or take margin of error. So we're going to have an interval estimation. And that's what confidence interval and confidence bound are all about. And what kind of tool do we use? We're going to use normal curve and normal approximation, but the formula differs a little bit. What was the formula that we used to use in chapter 6? Z equals n minus center over SD. But here, from chapter 7 and on, we're going to use standard error in denominator instead of standard deviation. And what is the standard error in this particular case? It's the standard deviation over square root of n, where n is a sample size. So this one over here, we're going to put 76 in this particular case. In chapter 6, you can assume chapter 6 formula was the one with n value equals to 1, so entire denominator just drops out. We're talking about individual speed of individual cars for chapter 6, so n value was 1. In this case, we are talking about 76 cars, so we need square root of 76 here. This structure here in the left hand side, z equals n minus center over SE, this will not change. This is formula number 1, and there are many different SE formulas based upon circumstance. Those are formula number 2. They all tie. You're going to see many of these. In chapter 7 and early part of chapter 8, SE will be SE over square root of n, and later on we are going to see different SE formulas. But those are case by case, and each case find that SE, and we are going to just put into this formula here. Okay, I think I spent a bit too much time talking about theoretical details, so let's begin with the first subproblem. Assuming the standard deviation is about 4.95 miles per hour, find a 95% confidence interval of the mean speed of the cars. We're talking about the interval estimate, and the structure is given by this kind of picture. How do you draw this kind of picture? The process is the same as before. Outline, center, end, and finally shade. Now outline, we have normal picture going up and down and symmetric, unimodal. Alright, and center is 62 miles per hour because that was the given mean speed here. Now end, there are two ends here because we are looking for confidence interval. This blue point x1 and this red point x2, and the middle part is the one we want. So shading should be done in the middle part, or if you have 3 different colors as we see right here, then you can use 3 different colors here. The main part is the middle part, and the middle part have to have the given confidence level of 95%. What does that mean? There's 95% of chance the real mean will fall in between this x1 and x2, right here in the middle part. So if you find out x1 and x2 and get this interval, what do we get? We have the interval estimate of the real mean. There's 95% of chance that the real mean will fall in this interval. That's what you're after. Okay, all right. And let's solve this problem technically. That's step 2. And which one do you want to find first, x1 or x2? Or if you want to use different characters, a and b, or mu1, mu2, anything will do. Let's find this blue. What do we use? We use the same formula here. N minus center over SE is appropriate z-score. Let me expand this font a little bit. Okay, that's large enough. And then let me put this picture right over here. Okay, that looks good. Now you're looking for this x1, this blue point. Well, 1 subscript 1 is a bit cumbersome, so let me just call it x. And x is the end, and center is 62. So what we have in the numerator, end minus center, we have x minus 62. How about SE is standard deviation over square root of n. So we have this formulation here, x minus 62 over 4.95 over square root of 76. And that should be equal to appropriate z-score you find from the z-table. And the z-table is associated to shading on the left-hand side, right? Shading on the left-hand side. Here is a z-table. Shading on the left-hand side. So you have to find out this shading, the blue part. Now 95% in the middle. By symmetry, we have to have 2.5% in blue and 2.5 in the red part. So let's use 2.5% here. So look up 2.5% from the z-table. So we have a bunch of numbers here. All these are probabilities for appropriate z-scores. And look up something closest to 2.5%. Found it? Negative 1.96. That is your z-score. Negative 1.96. That part came from the z-table. This completes the equation, and all you have to do is to solve this equation. It's not too bad. Flip this denominator, flip this denominator to the right hand side by multiplying it, and here we go. And then flip this subtraction by 62 to the right hand side. This is what we get. 62 minus 1.96 times SE. Run into a calculator, you get 60.88 something, 60.9 approximately. Now, how about the other endpoint? You can set up similar equation, but I found it a little bit more convenient to use the symmetry. Look at this picture. From 62, I went to the left, and that's associated to negative 1.96. Now I'm running to the right. That should be associated to positive 1.96. It comes from the symmetry. Run your calculator, you're going to get 63.1 approximately, like this. Let's go back. Initial picture, outline, center, and then shading. The middle part is 95%. So 2.5 in the left, 2.5 in the right. 2.5 in the left is more convenient to use. And look up 2.5%, you're going to get z equals to negative 1.96 from the z-table. And that is equal to end minus center over SE. Solving that equation, a bit of an algebraic process, you're going to get the x value. That's going to be your endpoint in the left-hand side. How about the right-hand side endpoint? Just use the symmetry. Instead of negative 1.96, positive 1.96, and you're through. Here is the conclusion. Therefore, the 95% confidence interval is about 60.9 to 63.1. You can use this kind of interval notation with bracket. Personally, I like to do that. Or you can use dash. You can use variety of symbols. And the final picture kind of looks like this.